Dear students, welcome to the first live session of the course Sustainable Power Generation Systems. Till today, we have covered 4 modules. 1, 2, 4 are the module numbers. And module 1, we have covered introduction to power generation methodology. Mostly in this module, global and Indian scenario of power generation, and then the energy mix were discussed, and also overview of current technologies available for power generation, and then concepts of renewable energy based power plants were introduced and discussed briefly. In module 2, solar thermal power generation systems were covered, and in this module, primarily we have addressed the fundamentals of solar thermal energy conversion, solar thermal based power plant design and analysis. It may be flat plate or maybe concentrator. Then organic Rankine cycle, the kind of organic fluid used in the cycle. Also, we have elaborated about the Rankine cycle and how this Rankine cycle and Stirling engines can be used for harnessing solar thermal energy. Then in module 3, primarily we have addressed solar PV power generation systems, starting with fundamental of solar photovoltaic energy conversion systems, solar PV power plant design that includes both standalone and grid connected PV systems, and it's all design methodology. And also we have solved sufficient number of numerical problems to understand how a solar power plant is designed, irrespective of its no type like standalone and grid connected PV system. And examples like, suppose if we are trying to build a water pumping system for irrigation, then we know the amount of water required, and to get that water for a particular paddy field, the amount of solar PV required was calculated and demonstrated as far as the design is concerned. Also, we have demonstrated how a grid connected PV plant is designed. Also, we have touched some of the important aspect of DPR preparation, like detailed project report preparation for a solar power plant design. And in module 4, exclusively, we have discussed wind power generation systems. So there, starting with the very fundamental concept, how this wind is measured and how wind is created, what are the performance parameters, what are different types of wind turbines, then wind blade geometries, then performance evaluation, then amount of power conversion by a wind machine, and then finally we have compared the performance of wind machines and its performance characteristics. Also, we have solved sufficient number of numerical problems to get an idea of wind power plant design. And at the end of this module, we have introduced the concept of wind farm. Now, what I would like to discuss is about some of the questions raised by some of the candidates. One of the questions, what I could see here is like in a combined cycle power plant, one gas turbine and one steam turbines are combined to produce electricity. The efficiency of gas and steam turbines are 40% and 50% respectively. So combined cycle efficiency need to be calculated. So this has been discussed in the class. So it can be written as combined cycle efficiency may be efficiency of ZT plus efficiency of ST minus efficiency of ZT multiplied by efficiency of ST. So if you substitute the values, so if it is 4 is the efficiency of gas turbine, that means 0.4, and for steam turbine is 0.5 minus 0.4 into 0.5. So resultant efficiency can be calculated. And the second questions, these are for assignments. So some of the questions, so in the portal, so they have typed wrongly, but now it has been rectified in assignment 1 and other assignments. But in many cases, what I found, people are getting confused with calculation of top loss coefficients. So maybe I take this for expansion, and maybe I will derive how we can calculate the top loss coefficient, bottom loss coefficient, and side loss coefficient. And finally, we can find out what is the overall loss coefficients. Let us do this. I'm hoping that you got an idea of energy balance on the observer plate. Say, for example, if you have this solar collector, this may be liquid flat plate collector, I should say liquid flat plate collector. So here you'll have different layers. Say maybe this is glass cover and this may be observer plate. And beneath to the observer plate, we'll have this tube through which heat transfer fluid flows. And this may be glass cover. And this is observer plate. And this is the tube through which heat transfer fluid flows. Okay, so solar radiation is falling, so short wave radiation is coming and it is transferring through the glass cover, and then long wave radiation is going back, and some are in the collector itself to provide the heat effect, right? So if I try to write energy balance equation on this observer plate, then what we can write, QU is the useful heat gain is equal to AP into S minus then QL, okay? So this has been demonstrated how this S can be calculated, how this QL can be calculated. So if we expand this UL, it is something like UL AP TPM minus TA. So this plate temperature is TPA and TA is the ambient pressure. Okay. So this UL is nothing but overall loss coefficients, and AP is the area of the observer plate, and TPM is the average temperature of the observer plate, and TA is the ambient temperature. So we can show that this UL is nothing but sum of UT plus UB plus US. Okay. So UT is top loss coefficient, bottom loss coefficient, and side loss coefficients, right? So how we can make it? we know this collector, if we say we have side loss, then we have bottom loss, and then top losses. So if I write again this configuration, okay. So if I have insulation here and here, okay, this may be your things. So this may be the things, and this is the glass cover. This is glass cover, and these are the insulation. So thickness of insulation we know for sides and bottoms. So what we can express, this QL is nothing but QT plus QB plus QS. Okay. So if we express this QT, QB, and QS in terms of loss coefficient, it will be something like UT, AP, then you will have TPM minus TA. Okay. Plus you will have UB, AP, TPM minus TA, and you have US, AP, TPM minus TA. Again, you know what is QL is nothing but UL, AP, TPM minus TA. Okay. So if we divide the entire expression by AP, TPM minus TA, then what we will have, UL is equal to UT plus UB plus US. Okay. Now, let us consider a condition like if you have two glass cover in the cover system and one absorber plate. This may be glass cover 1, this may be glass cover 2, and this is here TPM is the absorber plate temperature. So temperature of the glass cover 2 is TC2, glass cover 1 is TC1, and TPM is the main plate temperature, right? So when we are trying to see the losses like heat transfer by convection and radiation from the top. So what we'll have here, suppose if I write QT by AP, which is HP to C1. So from absorber plate to this glass cover 1, this is the heat transfer coefficient, and this is for convective part. Then we'll have a radiative component, sigma TPM to the power of 4 minus TC1 to the power of 4 divided by, if we know the emissivities of the plate and then emissivities of the glass cover, then for parallel plates we can write this expression. So this is one condition when heat is exchanging from the plate to the glass cover 1, and then from glass cover 1 to the glass cover 2, and then glass cover to the ambient, right? So you must know like the temperature profile. So it is something like TPM is greater than or equal to TC1 greater than or equal to TC2. This strategy you must know, otherwise you will fail to do the calculation, right? So let us again expand it. So here what I was trying to make you understand, from here to here, the kind of heat exchange taking place, what I have written here in equation 1. And next page, what I'm going to write is the heat exchange from glass cover 1 to the glass cover 2. Let us see how it look like. So it will be something like QT by AP, which is equal to TC1 AC1 to C2, then TC1 minus TC2 plus sigma TC1 to the power of 4 minus TC2 to the power of 4 divided by, this is for glass cover 1, and emissivity is for glass cover 2 minus 1. This expression is valid when two plates are parallel to each other. They view each other in this direction. And then again, what you can write, QT by AP is equal to HW TC2 minus T sky, then sigma TC, then TC2 to the power of 4 minus T sky to the power of 4. Okay. So here condition is we have to have same values of QT by AP for all these three expressions. Okay. Then what we can find out is the QT AP average. So if it is same or if it is very close by, say for example, in a situation you are getting a value of say 200 for one case, say watt per meter square, maybe 197 or 98 watt per meter square in the second case, and maybe 199 in the third case. Okay, then you can take average, and what you will get is the 199 is the correct value. Okay, so once you know this QT by AP, you know the expression how to calculate UT. Okay, because this QT by AP is nothing but you have UT, then delta T is the temperature difference. Okay, so once you know this temperature difference, then you can find out what is UT. And other expressions for calculation of UB and US is known to you. Then finally you can find out what is UL. It is nothing but UT plus UB plus US. Okay. Now condition is it is TPM temperature, average temperature of the plate. Okay. And also there are many unknowns like TC2 and TC1. Okay. But what strategy you could follow? As I said, TPM is greater than TC1 is greater than TC2. Okay. Say for example, if we consider a numerical problem, and if we say that this TPM is about say 70 degrees Celsius. So if it is 70 degrees Celsius, then in Kelvin it will be 273. It will be 3, 4, and then 3 Kelvin, right? So 343 Kelvin. And if we consider, say, 24 degrees Celsius is the ambient temperature. So this plus 273, which will be equal to 7, then 9, then 2, right? So this is Kelvin. Now, how are you going to select the appropriate temperature TC1 and TC2? You know TPM is 343, okay? And you know the perception, like how it will vary. Then you may consider 325 maybe TC1, or maybe 305 Kelvin is for TC2. Then what you need to do while calculating this TC1, TC2, or maybe plate to the glass cover 1, then we need to select the appropriate correlations. And if we know this distance between this observer plate, then glass cover 1, glass cover 2, and then if we know this temperature here and here, then in order to find out the air properties here, we need to take the average temperature of these two plates. So this may be, if we consider the air average properties to be considered or to be evaluated, then what we can do, it's the TC1 or GC1 plus T observer plate divided by 2. So at this temperature, we need to find out what is the air properties. So once you know the air properties, then what we can do, we can find out the heat transfer coefficient by considering an appropriate correlations, which will be given to you if we ask questions on this. And these are standard correlations to be used for these conditions when two plates are parallel. Okay. Then, so for example, if we have to use a correlation, something like it is assumed that we got a array cos beta value. So beta maybe, this is this angle beta. So array is release number, which is something like Prandtl's number into Grashof number. So Prandtl's number also we can get it at particular air temperature. So this is something like Prandtl number, we know at that condition, and Grashof number is something like beta z del t L cube by nu square. Okay, and this beta is something like what we have calculated. T average is something like Prandtl number 1 by t, and which will be in Kelvin. Okay, average 1, and then we'll have z is 9.81, and delta t, we know this temperature difference between these two plates. Then delta t we can get it, and L is the characteristic length between these two plates. So this is L cube, and nu what we will get at that particular temperature. So once you know, then we know these values, and once we know Ra cos beta, and this will be something like cos beta multiplication. So once we know Ra cos beta, then this will guide you the what correlations to be used for the particular calculation. Okay. Just I would like to give an example. Say, for example, if we get a value of say 61,544, which is Ra cos of beta. So then we need to use a correlation, something like Nusselt number is equal to 0.229, which is Ra cos of beta to the power of 0.252. Just for your understanding, I am giving one example. So if we calculate it after substituting the values of Ra cos beta, then this comes out to be 3.6873. And we know Nusselt number is H L by K. So here H is nothing but H plate 2 plus over C1. Okay. And then it will be 3.6873. And already know that at average temperature, what is K? And we know that difference between the two plates is L. So H can be calculated. Okay. So that's how we can calculate H. And then we can calculate other values as well by using the appropriate correlations. For example, if we have to calculate HW, then we have appropriate correlation. HW is about 5.7. This is plus 3.8 into U infinity. And this is the free stream velocity or wind velocity. And this correlation is coined by McAdams. So once we know this wind speed, then we can calculate what is HW. And also we need one temperature T sky, which is different than T ambient, TA minus 6. So once you know this, then you can calculate. And once we have this QT by AP, as I said before, then we can calculate what is UT. Okay. So once you know UT, UB we know, which is defined as thermal conductivity of the insulation and thickness of insulation. It is something like Ki by delta I. And US, side loss coefficients, we can write L1 plus L2 divided by L1 into L2 into delta S. And this is H, then Ki. So if I have to draw this, so this will be something like this. And then okay, so this may be H, and this may be L1, and this may be L2. So here, when we start with, say, Q side, S is something like 2. So there are, how many sides are there? We have this side, this side, and this side, and this side, right? So this area, this side area, and this side area is same. So that's how we can write 2 into H into L1 plus we have 2 into this side and this side. We'll have H into L2, right? So this is the area, or you can simplify further. This multiplied by, we'll have KI, then TPM minus TA. Then we have, this is average, and then 1 by delta S. So if you simplify it, then what we'll have, this is US. So once you know the dimension of the plate, we can find out, because already you have calculated the other values and these are known. So we can find out what is US, and finally we can find out what is UL, UB, US, and then UT. One thing we must know, this value, once we have calculated, this value should be in the range of 2 to 10 watt meter squared Kelvin. So if it is more than that, then your design is not perfect, and there will be a lot of losses. Okay, so we need to redo the calculations, and we need to modify the systems appropriately. On the top of it, also we have discussed this stagnation temperature, and why this stagnation temperature is so important. So this stagnation temperature is very, very important as far as design of a solar collector is concerned, because this is collected to see what maximum temperature that collector can attain. Fine. So this is the queries, we got it. I hope now we got an idea how this has been calculated for solving these total losses. So there are questions like, what shall be difficulty level of the final examination? So in my opinion, you should do or participate in solving all the questions what is raised in the assignments. Then that will be sufficient. And if you follow my along with that, you need to follow my video lectures, and I think that will be sufficient to score a good mark. And there's questions like, can you please share the detailed solutions of which assignment? Okay, I'll try to discuss with the forum, and then maybe I'll give the detailed solutions in the discussion forum. And there's questions like, what is the best book for sustainable energy technologies for engineering service examination? I'm not sure engineering service examination which book you should follow, but as far as my knowledge goes, if you read my video lectures or view my videos, then I think that is sufficient to get a comprehensive idea about sustainable power generation system. Apart from that, you can read some books related to solar, maybe wind, or maybe hydro, maybe take wave, then tidal, then hydrogen generations. There are plenty of books, but you have to read separate content in separate books. You will not get in a single book. Oh, what is a Fresnel collector? It's a lens. It's a kind of lens. Okay, Fresnel lens. So there, what happens? You'll have fragmented glasses. So this is not continuous. You'll have these fragmented glasses. Okay, they're fragmented glasses. Solar radiation falls, and then it is reflected to a receiver here, and then it is heated up. And if we have heat transfer fluid through this heated section, then you can get the energy out, and you can do the work of what is required for you. Then we'll have wind is created by solar energy or some other means. Of course, this is created by temperature difference, which is caused by solar radiation. Okay. And also, there's no movement of the sun in the earth, which is clearly explained in the video lecture. So you said there is a question, why only 3 numbers of blades are used in wind turbines? So that is your choice. Like you can go up to many numbers of blades, but no, as I have demonstrated in the video lecture, that is the optimum power harvesting is possible if we have 3 numbers of blades. So we have also demonstrated like what is the tip speed ratio. It is like you have optimized number of blades, and then the condition at which you will get maximum power. Okay, so for example, if we say consider only single blade, so you have this rotor, okay, and then normally what happens, we have this 3-bladed system. Okay, so now if we reduce to single blade, okay, only 1 blade is there, but we need, say for example, P is a 50 kilowatt I want. This is my what is called objective, to get 50 kilowatt of power. So we have 3-bladed system what is designed, but now I am planning to remove 2 blades and only 1 blade I want to use to get 50 kilowatt. Then what will happen? To get the same power, it has to rotate faster. Then only you will get. And if the system will rotate faster than the design, then what will happen? There will be catastrophic failure. Okay. So 3-bladed system, as per the mathematical expression, you can say it will give the optimum power, and then we have optimum tip speed ratio. And this has been demonstrated in the lecture. So please view the lecture carefully. So what is the temperature limit that can attain by flat plate collector? So if we are not using any reflectors, then the maximum temperature of what we can attain is about close to 90 degrees. We cannot go beyond that. So if we use reflectors, then of course we can increase more by spending some amount of money. What is nacelle? Nacelle is a platform. Okay, this is the nacelle, and we have, this is the hub. Okay, so blades are housed here. So these are the blades. Okay, so blades are housed here. This is the nacelle where generator plus what we have, gear train, and then shaft. So all are housed. So nacelles are so big for a big wind turbines. You can use this base as helipad. Okay, so it's so big, right? And it houses all those what is called components required for power generation. So there are some questions like, no, it seems, you have not studied the lectures properly. What is the principle of lifting? So see, I think you have seen the aircraft. So there, what happens? That area, what I was trying to give there, area of the no aircraft wing is very very big compared to turbo machines. Okay, so turbo machines, blades are something like this. Okay, it is very very cambered. But if you say like our aircraft wing or maybe we have, so this is no cambered is there, and we'll go next. Uh, so maybe if you have cambered blade, so it is something like this. Okay. So this is the chord light. This is slight camberness is sufficient to provide the sufficient lift. Okay, the suction side, and then you have no pressure side. So the pressure differential actually act to lift the what is called system. Okay. We'll get PPT and PDF noted lecture, and maybe this will be uploaded soon. So numericals are you are saying tough and lengthy. Celsius numericals come in exam. So see, my intention is not to disturb you. So why I am keeping this long numerical so that no you can get an idea how a power plant is designed. So anyway, it is not possible to design a power plant in a no exam. Okay, so there are might be some components in between the numericals which might ask in the exam. But now you must know how a power plant is designed. So when I say power plant, it's power plant means all the power plants. It may be thermal power plant, it may be solar, it may be wind, or it may be geothermal, it may be fuel cell and others. Okay. So best book for best uh, for preparation of GATE exam. See, these courses mostly we have covered very very fundamental things, and of course the applied things. Okay, so if you read it carefully, all the contents are there. So in a videos or video course of this kind, you will not get all the informations together. So here, if you are doing the course very sincerely from module 1 to module 12, then I think you will get enough material to get so many answers. I'm not saying in the gate paper which gate paper you are writing, but no, you can connect the things. Okay? Because these all are related to fundamental science applications, where all the components of engineering approaches are present. In my opinion, you should carefully attend all the video lectures, and of course, we are going to upload the PDFs of the lectures. So read it carefully. This will really help you in many dimensions. Yes, I'll ask and I'll try to give all the solutions in a stipulated time, and this will be shared in the forum. Yeah, as part of protocol of the system, they will do in the discussion forum. Yeah, regarding PDF lecture notes, a discussion is going on. We are going to upload those what is called watermarked PDFs soon, and hopefully we'll get it. If you don't have questions, maybe we can stop here. Yeah, this assignment to numericals 10, 11, 12. These are all related with the one what we have derived today, like UT, UB, and then US. So these all are connected there. So maybe you got an idea how we have solved this. If you need further explanation, maybe I'll do the same in the discussion forum. Yeah, solution will be given to you, and after the completion of the assignment due date, I think you have to follow the instruction what is displayed in the portal. There should not be any extension. So when date is mentioned, that is the deadline. No more extension will be there. And of course, numerical solution should be provided. If there is no questions, then we can conclude the session here. So thank you very much for attending this live session. And I'm happy that you have asked very good questions. And I really thank you for registering this in this course. And also I request you to see the lecture notes very carefully. So I have prepared very comprehensively. Hope this will be helpful for you in the coming years and in future. Thank you. Maybe in discussion forum you can post your things, and maybe next live session if you have some queries again we can discuss. But the discussion forum is more effective if you have to discuss some doubts.